So I'm going to try to use this thing because the stop cam thing, because it's just too hard to teach this class and not write stuff as I'm talking. You know what I mean? So it might be a complete disaster. Hopefully not, but if it is, it's okay. In any case, I'm going to put my note. My notes will always be in the Dropbox. Okay. All right. So last time,
Are we muted on the screen?
can you hear me in Brownsville?
Yes.
Okay. So last time we had started to talk about the Dirac equation.
You can't see what's
Right.
It's zoomed in or something.
It's too zoomed in. Do you know how to unzoom it?
Maybe there's a button that says zoom. Yeah.
No. It's okay. Let's zoom in. Let's zoom in. It's got little people on it.
Yeah.
Okay. All right. So we started by talking. We wanted to talk about the Dirac equation, right? And our main goals in this lecture were to find a representation of the Lorentz group for spin 1/2. Right. And our other goal was to write down or find an equation of motion and or Lagrangian for spin 1/2. Okay, so we're interested in, constructing a completely relativistic, equation for spin 1/2 fields. Okay, and last time we spent a lot of time, talking about how you construct these representations for vector fields or tensor fields. Right, we saw how 4 vectors transform. Okay, and what we want to do now is talk about fields that don't necessarily have vector indices, or fields that might have different indices, or are written in different ways. Okay, and so what we want to do is try to come up with an equation that explains the physics of a spin 1/2 field, right? And to do that, I'm just going to remind you of some things about the Dirac equation. Okay, so around the time, around the late 20s or so, late 1920s, the Klein-Gordon equation. So people were trying to come up with an equation that explained, that described relativistic particles, relativistic quantum particles. And one of the first things you come to is the Klein-Gordon equation, right? And usually you see it written something like this, right? And immediately you run into problems, right? Immediately you run into 2 major problems. One is you get negative energy solutions, right? Because the energy for a relativistic particle goes like is p squared plus m squared. Right? There's nothing to stop us when we take that square root to get the energy. There's nothing to stop us from taking the negative energy solution. Okay? And the other problem that you ran into, which was even a bigger problem, was negative probability. Right? And that just came from the fact that you took, in deriving this equation, you promoted the time dependence from linear dependence to a quadratic dependence. Right? And one of the first things you learn in quantum mechanics is that the Schrödinger equation has to be first order in time. Right? In order to preserve probability, it has to be first order in time. There's just no other way around it. Okay? So these were the two kind of roadblocks to coming up with a relativistic quantum equation. And Dirac started to look at this, and he started to think, well, if I start with the fully relativistic Schrodinger equation. Okay, and please, no, I'm not gonna, you know what, I'm not gonna write, so it's d psi dt, and then the fully relativistic would be p squared plus m squared times psi. Right, so the right-hand side's the Hamiltonian, left-hand side you have the time dependence. Okay. And so Dirac's idea was, is there some way that maybe we could write this quantity inside the square root as a perfect square, right? In other words, is there some way that maybe we could factorize that thing, right? And you know that, and so what he came up with was rewriting this thing, this p squared plus m squared, as, can you still see? Yeah. As a square of some quantity like this. All right? So he proposed that you could rewrite this p squared plus m squared as this quantity squared. Right? And then when you plug that in, you can take the square root, and what you find is that everything's linear, right? The time dependence is linear, and the spatial dependence, which is coming in through the momentum operator, is also linear. However, for that to work, when you square this thing out, in order to get p squared plus m squared on the right-hand side, these alphas and betas, or these alphas and beta, have to satisfy certain conditions. And those conditions are that the alpha I squareds, the beta squareds, they have to be 1. And the other condition is that the alpha i's and alpha I with beta have to anti-commute. Okay, so those are the conditions that you need in order to satisfy, the Dirac's, kind of guess at this. Okay? And along with those conditions, you also need the alphas and i's to be traceless and have eigenvalues equal to plus or minus 1. And for something to be traceless and have eigenvalues of plus or minus 1, it's telling you, obviously, that these things have to be even dimensional. Right? That's the only way that you're going to get, if you have something that has eigenvalues of plus or minus 1 along the diagonal, the only way you're going to get 0, in other words, trace of 0, is that these things are even dimensional. Right? But the problem is you go back to your the Schrodinger equation, and let me plug in the Dirac operator now. And so this thing is now looks like this, where I have alpha dot p and plus beta m, and it's operating on the side. Okay. The problem is now you look at this and you say, okay, these things have to be even dimensional. Okay. They have to anti-commute. They have to, the square of these guys have to be 1. And so this automatically right here, this starts to sound familiar because you say, oh, wait a minute, I know some objects that behave like this. They're, extended objects, if you will, they're matrices, right? It's the Pauli matrices, right? So you might guess these are, maybe the Pauli matrices will satisfy what you need. The problem is that you need 3 of these because you have 3, components of linear momentum, and you have 1 of these. So that means you need 4 matrices. And we all know that there's only 3 Pauli matrices, right? So that's a problem, right? So obviously it's not the Pauli matrices. And the other thing you notice is that, so what that's telling you is you have to go beyond n equals 2. Right? You have to go to the next simplest case, which might be, which is n equals 4. Right? So you're looking at 4 by 4 matrices. And if we have 4 by 4 matrices, that means that this guy has to have 4 components. Right? So you started with, initially we started with a spinner, with a two-component spinner, right? When we wrote down this equation here, we were assuming that this guy is a two-component spinner, right? Spin up, spin down, or some linear combination thereof. But what we found is that in order to make this thing relativistic, or Lorentz invariant, we have to promote our spinner to be 4 components instead of 2. So it turns out that you can write this in a little more compact way if you introduce, if you rewrite these alphas and betas in terms of some new, I'll call them 4 vectors, and we put it in quotation marks. Right? And these are what are called the Dirac gamma matrices. Okay? And we usually denote them as gamma mu. And the reason that they're nice is that they can, if you write them in terms of, if you write everything in terms of gamma mu, you can summarize all these conditions with one equation, right? And that one equation is the anti-commutation of 2 of these guys is equal to 2 times the metric tensor. Okay? So keep in mind what we're after. So we're after, fully relativistic equation for spin 1/2 fields, but we also want to be able to write down a Lorentz, a Lorentz transformation for these fields, right, or for these spinners. And it turns out, I don't want to spend a lot of time on it because you can get really bogged down in the details, but it turns out that you can write down an n-dimensional representation of the Lorentz algebra in terms of these gamma matrices. Right? So last time we talked about these guys, the S mu nu, right? These are the generators of, in general, they're the generators of your Lorentz transformations, right? They can be boosts or rotations. Right? And in the particular case of spin 1/2 fields, you can show that the commutator of gamma mu and gamma nu, multiplied by this I over 4, gives you the generators, right? In other words, remember that we had that condition that the commutator of 2 generators, remember this God awful thing, sigma rho, and there's 4 different terms, so it goes like I, G, nu, rho, S mu sigma, minus G rho, S mu sigma, minus G mu sigma, S mu rho, G mu sigma, S mu rho. Right, so remember this was the condition that, if your generators obey this equation, right, then they are, they're good generators, right? They're good, they form a representation of the Lorentz group. And it turns out that these gamma matrices, well, initially we introduced them to simplify, the form of the Dirac equation, or the form of the Klein-Gordon equation, as we'll see. But they also help you construct the generators that you need for the Lorentz group for spin 1/2. Okay? Like I said, there's a lot of details that I'm kind of skipping through here. And you're more than welcome to go off and study those aspects of it, but I don't want to spend a lot of time on it because I want to get to phenomenology. I want to get to the physics of it. Okay.
Excuse me.
Yeah.
If we go to general relativity, that metric tensor is different. So are these discussions also likely in the general relativity?
There might be some minus sign differences here and there. So you're talking. So what? Okay. So everything I do in this class, is going to be for what we call the East Coast metric. So it's +1, -1, -1, -1. Right? And zeros everywhere else. You guys have heard this in Brownsville?
East Coast and West Coast?
Yeah. No, you've never heard this?
No.
Oh, okay. So this is what's called the East Coast metric, and it's mainly used by particle physicists. Okay. So this is East Coast.
But I mean, in general, relativity is G, meaning it's not as simple as this. It has
Oh yeah. Oh yeah, off diagonal terms. Yeah, no, no, this is quantum field theory, so I'm not working in any curves, you know.
I mean, quantum field theory is written for the special case.
Yes. Yes. But just to finish off what I was saying, you have an East Coast metric and you also have a West Coast metric, which if you guys are in GR, you might use this one where it's minus plus
Yeah, I mean,
plus, right? So you have to always, you know, when you look up something in a QFT book or even a GR book, check in the front or the back and check the conventions, because a lot of times, you know, there might be a difference in the metric that you're used to. Okay, but in this class, particle physics, you should use the East Coast metric. Okay. All right, that's the only one that makes sense. All right. So we see what the advantage is of using these gamma matrices. Okay. And what do I want to do next? I'm trying to merge two sets of notes. First. First is supposed to be this. Okay. So I don't have the algebra here in front of me, but if you go through the algebra, okay, and introduce the gamma matrices here, okay, you can pull everything together. And I think I'll make this a homework problem since I'm not doing it in class. It's a good exercise. But you can go from this here, right, to this for the Dirac equation. Okay? And I mean, beauty's in the eye of the beholder. But you know, if I compare this to this, to me, this is nice, right? It's nice for one particular reason, right? Let me make it a little more explicit by defining what we call the slash notation, right? So A slash is a 4-vector A mu dotted into the Dirac gamma matrix, okay? So if I use this slash notation, I can rewrite this as I del slash minus n. So, okay? And now I look at this equation. Okay, so first let me look at this equation. I look at this equation. Is this thing Lorentz invariant? Who knows? Right? If I'm just looking at it, I don't know. I don't know what alpha and beta are. You know, there's a factor of momentum here. I mean, anything could go wrong, right? When I do a Lorentz transformation. When I look at this equation, and somebody asks me, is that equation Lorentz invariant? I can without a doubt say yes. Right? Right, because everything is a scalar here. Right? There's no open indices. So I know anytime I have a scalar, it's automatically Lorentz invariant. Okay? Right? And we talked about, even more general, if you have an equation that has even open indices, right? As long as the open indices match all throughout the equation, that equation is Lorentz invariant. Okay? All right, so before, let's see, what do I want to talk about? Okay, further. This one. Let's go ahead and get this out of it. Well, I don't think. Let's get to the solutions. Okay, let's talk about the solutions to the Dirac equation. Okay? And if I have, so what I have in the notes is a lot of stuff about proving that the Dirac equation is Lorentz invariant. But I don't think we need it. Okay? But it's in the notes if you want to look at it. All right? What I want to do is talk about the solutions. Okay, the solutions to this equation. All right, and the first thing I want to do is I want to replace this I del with momentum, because remember with I h bar with h bar set to 1, p is equal to what? It's I del mu, right? Am I correct in that? I can't remember the sign, but I think it's okay. So that tells me that I can rewrite this guy as p slash minus n operating on psi, and that thing is equal to 0. Okay? All right, so this is just the momentum space representation of the Dirac equation. Okay? And the thing to know, okay, so we started out by saying that this is the good thing about papers, is that I can go back and find something that I wrote, but the hard part is going back and finding. So we said, the Klein-Gordon equation was great. It's obviously Lorentz invariant, but it has some problems, negative energy solutions and negative probability. Well, we solved the negative probability by going to, to a linear equation in time, right, the Dirac equation. But the negative energy solution, that's coming from this dispersion relation, is still present, okay? So this thing still has negative energy solutions. Right? And we'll talk about those more in just a little bit. Okay? There's just no getting, this turns out that there's just no getting around them. It's a matter of how do you interpret them. Okay. So let's talk about, or try to, extract some physics out of this equation. Okay? And the best way to do it really is just to introduce a particular representation for our gamma matrices. In other words, write down a matrix form of the matrices and carry out this this multiplication. And so we know that they're 4x4 matrices, okay, and that means that the wave function, we're still here we're still talking about single particle case, so the psi is still the wave function, okay? We'll promote them to fields later on once we get the solutions, okay? So we want to write down the Dirac gamma matrices, right? It turns out that there's no unique way to write these guys down. Okay? There's no one particular unique way. The only thing, so there's no unique way. There's no unique, let's just call them set of gammas, right? Probably butchering some math notation, that's okay. Right? However, so you're free to choose. Right? This is America, so we should be able to choose however we want. Okay? Alright? The only constraint we have is that whatever we choose, we have to make sure that it satisfies the anti-commutation relation that these guys have to obey. Right? Okay. So there's one particular representation that a lot of people use, and you'll see why. And let me just write it down. Okay. So we know that these guys are 4x4 matrices. Okay. But the easiest way to write them down is what's called block diagonal form. Am I off? Okay. is to write them in what's called block diagonal form. Okay, what this does is it saves you from having to write 16 components, and you can knock it down to 4 components. Okay, so this one particular representation, gamma 0 looks like this. Okay, and these 1s and 0s represent 2 by 2 matrices. So this 0 is really zeros like this, and the 1 is just the identity matrix. You guys see that? Okay? And likewise, you can write the other guys, gamma 1. Okay? And remember, if you remember back to when you first studied the Dirac equation in quantum, you make a relationship, you find a relationship between the alphas and betas and the Pauli matrices. Right? And these gammas are built from the alphas and betas. So gamma 1 and gamma 2 and gamma 3 depend on the Pauli matrices. Okay, so this is sigma 1, minus sigma 1, 0. And gamma 2 is 0 sigma y minus sigma y 0. And gamma 3 is 0 sigma z minus sigma z. Now, I just noticed I used. Okay, so let's call this x. Mix notation. Okay? And this representation of the gamma matrices is called, and we'll see why in a minute, it's called the chiral representation. Okay, so it's one particular way that you can write down the gamma matrices. But if you look back in old books, most modern books, this is what they use. But there are books where you can go back and find different representations of the gamma matrices. Okay. Okay.
Can I ask a question?
Yeah, sure.
For Dirac equation in momentum representation, P dash minus 7,
Yeah.
P is sort of matrix. It's matrix with differential operators, and M is just nothing, right?
Yeah. So what's hidden here is an identity matrix.
Okay.
You see? Yeah, because it has to be a matrix operating on the 4 component spinner. Yeah, I should have mentioned that. And same thing here. Okay, so this is what trips some people up sometimes. Okay, so over here I have 2 4x4 matrices, right? But this thing is just the components. It's just the components of the metric tensor. So really what's hidden here is a 4x4 identity matrix. Okay? So there's always, I typically assign a homework problem where you're supposed to prove this, okay? Or at least show it for a couple of examples for different values of mu and nu. And people don't realize that there's a hidden identity matrix over here, okay? Because like I said, these are just the components. Okay. All right, so you got gamma 0, you got gamma 1 through gamma 3. It turns out that I can write this, if you look at it, you can see that I can write it in a little more compact notation. So I can still write gamma 0 like this, right? But all the gamma i's, if you will, I can write as a vector, right? And it's a vector of the Pauli matrices. Which sounds a little weird, but it's just, it's just a notation. It's just a notation thing, a simplifying notation thing, okay? And then I could actually rewrite this in terms of one gamma matrix. So I can call this thing gamma mu, and it's going to look like this. 0, and then sigma mu, and then sigma bar mu, 0. And you say, what are these sigma mu and sigma bar mu? Well, they're sigma mu it looks like a 4 vector, right? But it's a 4 vector made out of 2 by 2 matrices. Okay? So it's an identity matrix in what you would call the time component, and then the vector sigma. And then sigma bar is 1 and minus sigma vector. Okay, so this is all just to simplify the notation. So I start out by picking a particular representation. I can write it in block diagonal form. Right? And then I notice that this thing looks like, if I combine the different components, it looks like a vector. Right? So I can combine these three in terms of a vector gamma matrix, if you will. And then finally I can combine these two into a 4-vector gamma matrix. Okay? Right? So these are all useful identities. Okay? But like I said, it's just notation and it's just to simplify stuff. Okay. So let's go back now, and what we want to try to do is rewrite the Dirac equation using these gamma matrices. Okay. So let's see. Okay. So I've got. Let me start with p slash minus m operating on size. Okay. And so let me plug in. So this is, if I expand it out, it's gamma 0. P0 minus gamma I, let's call it, gamma I, it's gamma vector divided into P vector, and minus M, okay, on the side, okay? And now let me plug in the matrix representations of these, okay? So gamma 0, I would get something like this. I have 0, P0, P0, 0. Okay, that's that piece. And then the other piece is 0, sigma dot P, minus sigma dot P, 0. Okay, and then here's where I have to remember that the M is multiplying an identity matrix, so it's M, 0, 0, M. Okay, so that's what the operator looks like now in matrix form. Now, since I've broken, so these are 4x4 matrices, right? But I've written them in a shorthand notation in block diagonal form, right? So it's 2x2 sub matrices, right? So let me do the same thing. Let me take this four-component spinner and rewrite it in terms of two-component spinners. Okay, and for reasons unknown, I'm going to call one of these side L and the other one side R. Okay, and then on the right hand side I still have 0. I'm just picking L and R out of a hat. Just two letters at this point. Okay. All right, so I can combine this into now one big matrix. So on the diagonal piece, the diagonal components, I just have minus M. And here I have P0 minus sigma dot P. And here I have P0 plus sigma dot P minus M. And then this is operating on side left. Side L and side R. Okay. And now, so this is representing two equations, right? All right, I can multiply this out and get two equations. So let me do that. So let me multiply it out. And when I do that, I get P0 minus sigma dot P hitting psi R. And that's equal to plus M psi L. Okay? And likewise, from this bottom row, I get P0 plus sigma dot P hitting psi left at L equals M psi R. Okay? All right, so think about what we've done here. So we started with, 4x4 matrices acting on a 4-component spinner, and we weren't sure how to interpret the 4-component spinner, right? But we introduced a particular representation of the gamma matrices in block diagonal form, and sure enough, we get back two equations, and now these guys are 2-component spinners, right? And we know how to work with 2-component spinners because we've been doing it since, since kindergarten, okay? All right? So these are 2 equations, okay? They're obviously coupled. And they're coupled, we say they're coupled through the mass term, right? So you see this mass term here is multiplying, so for the equation for psi r, it multiplies psi L and vice versa for the other equation. Okay? So these are the general equations. So let me keep these handy. Okay? But what I'm going to do now is go to a specific kind of extreme case. I want to go to the case where we're talking about massless particles. Okay? So I'm going to set the mass terms to 0. So let me rewrite it. P0, P, psi r, that's equal to 0. P0 plus sigma psi L. Okay? And in that case, when we set the mass to 0, we see that the equations decouple. Right? And these are an important set of equations. Right? They're called the Weil equations. Okay? And they're important because they're useful for describing neutrino physics. Okay? There you have basically massless particles. Okay? And so what we see is that for the case of massless particles, our 2 equations, or really our Dirac equation, splits into 2 separate equations, right? 2 different types of particles. Okay? And these particles, you might find this surprising, but R means right-handed. Okay?
Yeah.
And with L, I know this is surprising. It's left-handed.
Impossible.
I know it's a real coincidence, right, that I picked R and L at the beginning, but that's the way it works out sometimes. Okay, sometimes you get lucky. So what do we mean by left-handed and right-handed? Well,
Can you move it down?
Down.
Drink of water.
yeah, so I just took the mass to 0 in those previous equations. Okay. And what I see now is that the equations decouple, and we're calling these guys by 2 different names because they satisfy 2 different equations, right? So they're 2 different basically 2 different particles. And what do we mean by left or right-handed? Well, we mean that they are eigenstates of what we call the chirality operator. Chirality operator. Right? And this chirality operator is a new gamma matrix, basically. And it's called gamma 5. Okay? And the way that you construct gamma 5, there's a couple different ways, but the standard way is you take all the gamma matrices, gamma 0 through gamma 3, and then you multiply them together, and then you multiply by a factor of I. And when you do that, you see that gamma 5, you can represent it in matrix form, in block diagonal form like this. Okay? So take Mathematica or whatever you want, and plug those gamma matrices gamma matrices in, multiply them out, and you end up finding that gamma 5 takes this simple form. Okay? And now you see why we call these things left-handed and right-handed, right? Because gamma 5, if it operated on a purely, and what we call left-handed and right-handed is just convention, right? It's just that they transform differently, or they have different eigenvalues under this chirality operator, right? But if I operate on a purely, what we call left-handed state, so that would be a state where you would have psi left, you had psi left, but a 0 and then psi right component. And I plug this in, I see that I get a minus, minus psi L. And so that tells me that this guy, psi L, is a eigenstate of the chirality operator, and its eigenvalue is minus 1. Yeah. And likewise, if I operate on a purely right-handed state, right, I get plus 1. Okay, so these things have some idea of handedness, you know, when you go back to right-handed or things like that you learn in undergrad physics. Okay. All right, so this gamma 5 is a useful quantity. It's useful because you can construct projection operators. Right? So say I'm given some general, 4-component spinner, and I want to project out the purely left-handed part of it. Okay? So the way I could do that is by defining some operator that when it hits this guy, it just gives me psi left. Right? And you can show that this guy you can write in terms of gamma 5 as 1/2 1 minus gamma 5. Okay, where this 1 is the identity operator. Okay. And likewise, you can write down an operator that when it operates on the general 4-component vector, you get the right-handed component, pure right-handed. And this guy is 1/2 plus gamma 5. So gamma 5 is useful, and we'll see it more when we get into the phenomenology, because it has a lot of weird and wacky characteristics that you have to deal with. Okay. Okay.
Can I ask a question?
Yeah.
Where is gamma 4? We have gamma 7, gamma 3. Where is gamma 4?
That's a good question. I don't know the answer to that.
I thought maybe I heard that an old notation might have gone from 1 to 4 instead of 0 to 3. I could be wrong, but that's. I thought.
Yeah, I mean, I would guess that that's because the normal gamma matrix or gamma operator or whatever has 4 components. Right? But yeah, that's a good question. There's a gamma 6, but that doesn't really help us with gamma 4. All right.
I'm not sure.
Good question. Okay. So let me go back. And this is where this should be defined. This equation. Okay, so let me go back to the Weyl equations. Okay. And let me rewrite them in a more suggestive way. Okay. So remember that for cases where m equals 0, that means that E, the energy, is just magnitude of momentum. Okay. We're working in units where C is equal to 1 out of 2. Okay. So I can take this guy. So P naught here is the energy, but I can rewrite it as the magnitude of the momentum. Okay, so I can rewrite these equations as the first one is sigma dot P all over the magnitude P operating on the side R, and that's equal to sine R. And then likewise I can do sigma dot P all over operating on the side left, and I get minus 7. Okay? And these have the form of an eigenvalue equation, or eigenvalue equations, right? It's saying that when I operate on side R with this operator, I get a +1, and when I operate on this side left with this operator, I get a -1. Okay? So they're both eigenstates of this operator, and this operator is a special operator. It's called helicity operator. It's called the helicity operator. Okay? And if you go back and you look, well, if you go back, I got one.
Like gamma 5.
Yeah, it's just like gamma 5, exactly. That's the point I'm trying to make, but I was trying to find my sheet. But I found the one for R, right? So if you compare this with these two guys, right? This guy we call chirality, and this we're calling helicity. Well, it turns out that for a massless particle, those two quantities are the same thing, right? However, for a massive particle, that's not the case. Okay, so a massive particle will still have some chirality that will be constant. You know, that's intrinsic to the particle, right? It's either left or right-handed particle. Okay. However, the helicity is not really how do I want to say it? You can always boost to a frame, right? So you can boost since it depends on the momentum, right? The direction of the momentum, right? Through this dot product. You can always boost to a frame where, so I can do a boost, where I take P, you know, I go to a frame where P goes to, say, minus P. Okay? But the spin is just what it is. So the spin's intrinsic, so it never changes, right? So the spin. Okay? But what it tells me is that the helicity, which let me just denote with a little h. Okay? It tells me that the helicity operator, which is this stuff here, it changes sign. Okay, so for a massive particle, you can always boost to a frame where you flip the sign of the momentum. All right. So what would happen is a right-handed particle would have a minus sign here, right? And a left-handed particle would have a plus sign. Okay. So the helicity depends on the frame. It's frame dependent. All right. Okay.
How did you derive those equations?
These guys.
Yeah.
Yeah, I just started from the Weil equation, this one. And so I took out, so P naught, I identified P naught as E, right? And E is just the magnitude of P for a massless particle. Okay, so then you got it? Okay. Okay. Alright, so let me just. Okay. So that's the case for massless particles. And like I said, those equations, the Weil equations, are useful, and you'll see, you know, when you see discussions about neutrino physics, you'll see the Weil equations popping up. But let me really quickly go back to the massive case. Okay. Alright, so let me go back and rewrite, because I'll never be able to find the equation, so let me rewrite it. Sigma dot P. Sorry, R is equal to M. And P naught plus. So there. Okay, so this is what we have for a general case, a general massive case. And you see that, you know, the Dirac particles in this case, right, the particle that, that obeys this equation and the particle that obeys this equation, they're admixtures of the left and right-handed pieces. And these pieces, like we talked about earlier, are coupled by the mass. Okay, so the way you can think about these states is that, you know, your state psi is some linear combination of psi left and psi right. Right, some linear combination of these left and right-handed chirality states, right? And because they have a mass, they're basically oscillating. They basically oscillate back and forth between each other, right? As you know, as a function of time. Okay.
In this case, the gamma phi, when this side is not the eigenfunction of the gamma phi.
Right. Psi. Yeah. Psi would not be. Yeah, because it's a mixture of the chiral states.
So the chirality is not defined from the mass.
That's not. Yeah, you're right. You're right. Yeah, it's not defined for the massive part. Yeah. Yeah, the chiral state. I think the chiral states are massive states. Yeah. Does that answer your question?
Yeah. Yeah. It's also defining the chirality is useless since we have density and chirality for massless particles is the same.
So chirality is useless? Well, it's not useless because, like I was saying, it's frame independent. Okay, so the chirality is what it is.
But if it's just for the massless particle, for the massless particle chirality and density are the same.
Yeah.
So
Or maybe you prefer chirality instead of, I don't know. No, I don't know.
Helicity does depend on
For massive particles.
yeah.
For massive particles. Yeah. But for the massless case, they're the same. They're one and the same. Or at least they have the same eigenvalues.
Maybe the concept.
Yeah. I mean, chirality, like I said, is a intrinsic quantity, right? It's you know, a particle is either right-handed or left-handed. The helicity has to do with the projection of the momentum on the spin, right? So if the particle is moving this way and the spin's this way, then it's going to have, you know, helicity minus one, right? And that's important, you know, when you're writing down processes, especially when you're dealing with, you know, chiral states. You want to make sure that you conserve, you know, the helicity, right? Things like that. Okay. Which we'll see more of later. But no, that's a good question. But no, chirality is not useless.
Is there some type of exclusion principle for chiral particles or something like that? Like, is there any physical difference
Is there any physical difference?
in different chiral?
Yeah. I mean, you have to write down an interaction that is chiral in itself, right? So you have to write down. Well, this is getting way beyond But yeah, you can, in an experiment, you can distinguish a left-handed from a right-handed particle. Right? It has to do with the exchange of the W boson. Right? So that interaction is chiral, right? It has a gamma 5 in the interaction. Okay.
Q first, left hand.
Mm-hmm. Yeah. Okay. But we'll get into that later. Okay. All right. So that's just I just wanted to point that out. Okay. So for the massive case, we see that the solutions are basically linear combinations, and because of that mass term, they basically oscillate in between the left and right hand states. And the last thing I want to do is turn to what we call the anti-particle solution. All right, so we said earlier that the dispersion relation is still E squared is equal to P squared plus M squared, and so when we take the square root to get the energy, there's nothing to stop us from picking the minus sign. Okay. And so that's what we're going to do. Right, so I'm going to rewrite. What am I going to do? So I'm interested in the negative energy solutions. Okay, so I'm going to rewrite the energy. I'm going to rewrite the energy term in the Weil equation or in these couple equations as minus magnitude of P naught. Okay. All right, so let me do that. Let me replace it, and let's work with the massless particles to make life simple. Okay, and so if I do that, my equations become minus sigma dot P operating on side R equals 0, and minus sigma dot P. Okay. And now let me solve or rewrite those like I did earlier, and write it in terms of the helicity operator. Okay, so these are what we would call they're negative energy solutions, so we're calling them antiparticles. Okay. Let me solve this for the helicity operator. I get sigma dot P all over the magnitude of the psi r equals minus. And likewise for this guy.
You need to know the
Sorry. Plus. Okay, so this is for the antiparticles. Right? You say, so what? You go back and you look at the solutions for the particle case. Right? Can you see both yet? And you see that compared to the particle case, the antiparticle, so these are the antiparticles. The helicity eigenvalues are opposite of what they are for the particles. Okay. Right. Okay. I think that's where I want to stop. So to summarize, go way back here. If I can find it. So we started out with the Dirac equation. Well, we started out by saying that Klein-Gordon equation's got some problems, right? But we could use Dirac's idea of writing this thing under the square root as a perfect square, right? In terms of these alpha and beta things. And if we do that, we can get, we have to impose some conditions on the alphas and the betas, but we can get something that's linear in both time and space. Right? And that's good because that tells us that we're on the right track as far as special relativity goes. And these guys we can replace with these Dirac gamma matrices, right? And from these conditions, we know that the alphas and the betas, or the gammas, have to be 4-dimensional. So that means that we have to promote our spinner, our two, what was originally a 2-component spinner, we had to promote it to 4 components. But then we said, okay, well, let's write down a specific representation of, I don't know what I'm of the gamma matrices. There it is. Okay, called the chiral representation. And when we do that, the equations we get, so we can write down basically 2 equations. So the Dirac equation breaks down into 2 equations in terms of 2 component spinners. Okay? If we take the massless case, it simplifies to what we call the Weyl equations. Right? And we talked about that these guys have definite chirality at the massless states. And that while the massive case, the mass term means that you have mixing. Right? You have a mixing term. And so they're not pure chiral states. And then we also talked about helicity, and I think that covers everything. So next time what I'm going to do is we'll start to construct the solutions for the spinners, okay, for the 4-component spinners explicitly. Okay. All right. Any questions about this stuff? I have some new handwritten notes. I'll scan them and put them in the Dropbox along with the old notes that were in there. Okay. All right. Okay. All right. So I'll see you Monday. I guess that's when the homework's due. But just let me know if you have questions about anything. Just shoot me an email. Okay. All right. See you guys.
That was a couple of quick questions.
Yeah.
The showed in previous lesson that when you have the distance equals I realized later that I was a little confused about functions like if we end up taking the P. Say, it's negative.
That's just because it's just a dummy index.
Yeah. So that wouldn't change.
Well, it would change. So you would have if you had a commutator between AP and say A dagger minus P.
Yeah.
Then you would have P plus P prime.
Okay, and this may be, I may be on the wrong track. I don't know, but for one problem, I ended up getting like several different what we call the bracket, commutative. That's right. Where and a few of them will like say have like an A. So ignore that minus sign, but like an A and
Another
A and not the without the diagonal. I was just couldn't figure out where I couldn't find anywhere that said what, if anything, that
It's
would
0.
be. I thought it might be, but I couldn't confirm it, so I wanted to ask.
Yeah, all the A's commute with each other. All the A daggers commute with each other. The only ones you have to be worried about are the A and A dagger.
Okay.
And they only don't commute at when they're at the same.
Okay, I think that should help me with everything. Thank you.
Okay. Thanks, sir. Yeah.
Yeah, thanks. I would have.